Hello everybody. So today we are going to discuss another important topic, that is action potential in neuron. So before discussing action potential, I hope all of you remember the concept of the last class, that is the resting membrane potential. Okay. So suppose this is a neuronal cell, although this is not looking like a neuron, but suppose that this is a neuron. So what will happen? The interior of the cell will be negative and exterior will be positive, and if we make comparison between inside with respect to outside, then that is minus 70 millivolt, and that is nothing but the resting membrane potential of neuron. Now I told you repeatedly that resting state means when the cell is not getting any form of stimulation or inhibition. So now you think of that the cell is getting some form of stimulation. So what is going to happen? So whenever the cell is getting a form of stimulation, the interior of the cell will be more and more positive with respect to outside, or you can say the interior of the cell will be less negative, like for example from minus 70, maybe minus 65, maybe minus 60, maybe minus 55. So these are the less negative potential. Less negative potential means I can understand that the interior of the cell is becoming positive. Interior of the cell is becoming more and more positive. This more and more positivity of the cell, okay, is known as depolarization of the cell. This is known as depolarization of the cell. Right. Now, rather than stimulation, if the cell is getting inhibition, suppose the cell is getting inhibition, any form of inhibitory stimulus. So the interior of the cell will be more and more negative with respect to RMP. Means if the RMP is minus 70 millivolt, the cell will be more and more negative, like for example minus 75, maybe minus 80, maybe minus 90, etc. So this kind of more and more negativity of the membrane potential, okay, is known as hyperpolarization. So this is known as hyperpolarization. Getting my point? So this is very simple concept, that more positive with respect to RMP, that is depolarization, and more negative with respect to RMP, that is the hyperpolarization. Now always I told you that if you want to record the resting membrane potential on a screen, then we generally use the cathode ray oscilloscope, CRO. So in this CRO screen, if you want to record the RMP, how this depolarization and hyperpolarization will look like, right? So suppose this x-axis, this is the time axis, and y-axis is the membrane voltage axis, right? So this is the point of RMP, that this is minus 70 millivolts. So this is my RMP. Now whenever I'll give a stimulation, suppose I'm giving a stimulation here. So what will happen? The RMP will move more and more towards positive side, more and more positive side. This movement of RMP towards positive side is known as depolarization. Now, obviously, if the stimulation is very, very high, okay, then this depolarization can give rise to an propagated potential, and that is known as action potential. We will be coming to that, but for the timing, you remember that if the depolarization is sufficient enough to cross a threshold, then a propagated action potential will be generated, and that is known as action potential, right? Now suppose the depolarization is moving more and more, and then the depolarization is crossing this 0 millivolt, 0 voltage, right? So this is 0 millivolt voltage. 0 voltage is also known as ISO voltage. So depolarization is becoming more and more stronger. It is going above the 0 millivolt, suppose. So the part of the depolarization which is going above the 0 millivolt, this is known as overshoot of membrane potential. This is known as overshoot of membrane voltage. So that part of the voltage which is going above the 0 millivolt, that is known as overshoot of membrane voltage. So very simple. So resting membrane potential is going for more and more positivity, that is depolarization. Whenever it is going above the 0 millivolt, that is known as overshoot of potential. Now, when this depolarization is again returning back towards the resting membrane voltage, okay, so suppose the depolarization has already been done. Now the cell is again returning back to the resting condition. So when the RMP, okay, when the membrane voltage is again returning back towards the RMP, this movement of membrane voltage is known as repolarization of membrane voltage. This is known as repolarization. So getting my point. So repolarization is nothing but when the membrane voltage again returning back towards the original condition. Original condition means towards the resting membrane voltage, that is known as the repolarization. Right? So more positive is depolarization, coming back towards the RMP, repolarization. Now if the membrane is becoming more and more negative due to inhibition, so the membrane voltage is going for more and more negativity. Maybe I told you, maybe minus 80, maybe minus 90 or whatever. This kind of negativity of the membrane voltage, okay, with respect to this resting membrane potential is known as hyperpolarization. Hyperpolarization. Again, if the membrane voltage is returning from hyperpolarization towards the resting voltage, again that will be known as the repolarization, right? So this very basic concept you have to remember. Now another thing is that depolarization is also known as decrease in membrane voltage. A little confusing, but try to understand. So whenever the membrane voltage is going for more and more depolarization, look at this diagram. So the membrane voltage is going for depolarization. This is the depolarization is going on here. If I want to comment whether the membrane voltage has decreased or increased, you have to look at the distance of this membrane voltage from iso voltage. What I told, look at that this membrane voltage, how far it is located from this zero voltage or iso voltage. Again I am repeating. So if you think of, okay, so just give me one moment. So suppose your membrane voltage is at minus 70. So from this iso voltage, if I measure the distance, this is the distance. Okay, so from zero voltage to membrane voltage, that is the distance. Now when the membrane voltage is going for depolarization, it is getting close to the iso voltage. It is getting close to the iso voltage. Now if I look at the distance from this iso voltage after the depolarization, so obviously the distance from iso voltage is reduced. That's why this reduction of distance from iso voltage is known as decrease in resting membrane potential. So basically I can conclude like this, that if there is depolarization of the membrane voltage, then the distance from the iso voltage is reduced, and that's why this is also known as decrease in resting membrane potential. So please remember that depolarization is equal to decrease in resting membrane potential, because in MCQ they may give you option rather than depolarization, they may give you option like decrease in RMP or increase in RMP. So that is why you have to remember. Now whenever the membrane voltage is becoming hyperpolarized, right, now you look at the distance from iso voltage, I can easily understand that the distance from iso voltage is very high whenever the membrane voltage is going for hyperpolarization. That means hyperpolarization means membrane voltage is going away from zero voltage. That's why the distance from the zero voltage or iso voltage is increased, and that's why hyperpolarization is also known as increase in resting membrane potential. Okay, just a little bit peculiar if you think normally, but this is the concept that you have to remember, because we cannot change this concept because this was been discovered by Nobel laureates. Okay, we are not here to change the concept. So decrease in RMP is equal to basically depolarization, and increase in RMP is basically your hyperpolarization. Right, now with this basic concept of change in resting membrane voltage, we are now going to discuss about action potential. So how the action potential will originate, right? So I am first drawing one neuronal cell body. Okay, so this is the neuronal cell body, right? Okay, so neuronal cell body means if I look at the membrane voltage, so inside is positive, inside is negative, outside is positive, and this is nothing but minus 70 millivolt. That is my resting membrane voltage, right? Now, suppose one neuron is giving stimulation on this cell body. How it will give stimulation? Obviously, this green color neuron which I am drawing here, this must be an excitatory neuron. This must be an excitatory neuron. In the central nervous system, we will read about this excitatory neuron, that they contain certain neurotransmitter, mostly glutamate, and that glutamate will act on this postsynaptic membrane, and the postsynaptic membrane will get stimulation. So this postsynaptic membrane will get stimulation because of this excitatory neuron. Stimulation means what will happen to the membrane voltage? If we look at the membrane voltage will change gradually towards depolarization. Like for example, it may go up to minus 65, maybe minus 60, maybe minus 55, or maybe more positivity, right? Whenever the membrane voltage is crossing this minus 55 millivolt. Note down, this minus 55 millivolt is very important for neuronal cell membrane. Why? Because this minus 55 millivolt is known as the threshold voltage of neuronal membrane. What do you mean by threshold voltage? Threshold voltage means, just hold on, threshold voltage means if you cross this threshold voltage, the action potential is going to be generated. But how? So just look at what I told. So whenever one neuron is giving stimulation on the cell body or dendrites, then the postsynaptic membrane will be more and more positive. Okay, so more and more positive means the membrane voltage will gradually rise from minus 70 towards minus 65 to minus 60, maybe minus 55, or maybe more than minus 55, right? Whenever the membrane voltage is crossing this minus 55 millivolt, this minus 55 millivolt is known as the threshold voltage. Threshold voltage means whenever you cross this voltage, almost all the voltage gated sodium channel, which are present at this area means this is nothing but the initial segment of the neuron. Could you identify the initial segment? The initial segment is that area where voltage gated sodium channel concentration is high, second highest, and it is the site where action potential is initiated. I told you in the previous classes, right? So whenever the membrane voltage is crossing this minus 55 millivolt, okay, almost all the voltage gated sodium channel which are present at the area of the initial segment, they will open up simultaneously. Look at my word. All of this voltage gated sodium channel will open up simultaneously, due to which huge amount of sodium will enter inside the cell, and this huge amount of sodium will rise the membrane voltage to plus 35 millivolt. Okay, so this huge amount of sodium is rising the membrane voltage, the interior of the cell membrane voltage is rise up to plus 35 millivolt, and this rise of membrane voltage suddenly from minus 55 to plus 35 millivolt is nothing but known as action potential generation of membrane. This is nothing but action potential generation. So what I told, if I just revise quickly, so whenever you give a stimulation, what will happen? The membrane voltage will gradually rise towards the threshold voltage. Okay, so if the membrane voltage is minus 70, it will gradually rise towards threshold voltage. Whenever you are crossing the threshold voltage, almost all the voltage gated sodium channel which are present at the level of initial segment, they will open up suddenly. Huge amount of sodium will influx, and due to which the membrane voltage will suddenly shoot to plus 35 millivolt, and that is nothing but action potential generation. So action potential is nothing but change in membrane voltage suddenly from threshold to plus 35 or maybe plus 30 millivolt, right? Getting my point? So now we are looking at this depolarization. Okay, so we have already discussed when the membrane voltage is rising from minus 70 to minus 65 to minus 60 towards minus 55 millivolt. This is nothing but a depolarization, right? This is nothing but a depolarization. this depolarization is known as local potential. This is known as local potential. Local potential is also known as graded potential. Local potential is also known as graded potential. Now, could you recall something? I told you in previous classes that site of generation of graded potential. What I told that site of generation of graded potential either at the level of dendrites or at the level of cell body or soma. Right. So this is the graded potential. What is this graded potential? This is nothing but a local potential. This is nothing but a depolarization which is generated on the membrane of the cell body or on the membrane of the dendrites. But because most of the synapse in the central nervous system forms on dendrites, so the more common site of graded potential generation or local potential generation is on dendrites. Now, why this potential is known as local potential? Why this potential is known as graded potential? Right. Let's try to understand that. So, if I try to plot a curve, okay, if I try to plot a curve of this local potential, so this is the membrane voltage, resting membrane voltage, that is minus 70 millivolt. Now, you are giving stimulation from this point. Whenever you are giving stimulation, the resting membrane voltage is moving towards more and more positivity. It is moving towards more and more positivity, and it is getting close to this minus 55 millivolt. It is getting close to this minus 55 millivolt. Right. This we have already discussed. Now, at any point of time, if you stop stimulation, at any point of time, if you stop this stimulation, what will happen? This depolarized voltage or this local voltage, again it will return back towards the RMP. So again I am giving stimulation, it is rising, and whenever I am stopping the stimulation, this local voltage is again returning back towards the RMP by gradual decrement. So what is happening? I can understand that this depolarization is a non-propagated potential which is remaining in the same places. It is not moving. If you stop stimulation in between, it cannot move from this neuronal cell body. It cannot move from here to the distal part of the neuron. If you stop stimulation, the local potential will die at the same area. It will vanish at the same area. Means it is not moving to a distal places of the neuron. It is remaining in the same localized area, and that's why we use the term that the local potential. So I can understand that the properties of this local potential or graded potential, number one, it's a non-propagated potential. It's a non-propagated potential, right? So local means it's a non-propagated potential. It will remain in the same localized area. It cannot move from one part of the neuron to a very distal part of the neuron. Then second, why then it is known as the graded potential? Okay, now look at this diagram once again. If you give a more stronger stimulation, okay, if you give a more stronger stimulation from this neuron, what will happen? The membrane voltage will be more and more positivity. If I give less stimulation, less positivity. If I give more stimulation, more positivity. Means in this curve, I can understand that less stimulation means less positivity, more stimulation means more positivity. Means the local potential is rising gradually in a step-by-step fashion. And this rise of local potential, this rise of depolarization depends on the strength of stimulus in a graded manner. Getting my point? Okay, more stimulation, more rise in local potential, more stimulation, more rise. So this rise of local potential in a graded manner depending on the strength of stimulus, that's why this is known as graded potential. So the graded potential means, okay, amplitude of the local potential, amplitude of local potential depends on strength of stimulus, depends on strength of stimulus in a graded fashion. That's why this is known as graded potential. Okay. Now the third point I have already discussed, that if you stop stimulation in between, so the local potential was rising and I have stopped the stimulation, suddenly what will happen? The local potential will die out. The local potential will decrease to the RMP again. So this kind of property is known as decremental property. So local potential is a decremental potential. Decremental potential, right? So the local potential is a decremental potential. And the fourth property is that local potential does not follow all or none law. It does not follow all or none law. All or none law you will understand a little bit later. Okay. So for the time being, you remember these are the four properties of local potential. Now whenever this local potential will touch this threshold voltage, whenever this local potential will touch this threshold voltage, I told you already that at this point huge amount of voltage gated sodium channel will open up, due to which the membrane voltage will shoot to plus 35 millivolt, and that is nothing but generation of the action potential like this. So whenever this action potential will be generated, the property of the action potential is just opposite to this four property that we have written here. What do you mean by that? Means action potential, whenever it is generated, it will be a propagated potential. It will be a propagated potential, means it will move from one portion to the other distal portion of the neuron in a same manner. Second, it's a non-graded potential. Non-graded potential means whenever the amplitude is generated up to plus 35 millivolt, further increment of amplitude is not possible. That is a non-graded potential. The amplitude is not dependent on strength of stimulus. And the third one is a non-decremental potential. It's a non-decremental potential, means if the action potential is moving from one part to the other part of the neuron, the amplitude will remain same. That means it will remain plus 35 millivolt only. The decrement of this amplitude is not going to happen. That is the meaning of non-decremental potential. And obviously, the action potential will follow. Action potential will follow all or none law. All or none law. What do you mean by all or none law? Means all means if the action potential is happening, it will happen with maximum amplitude, and if it is not happening, it will not happen at all. All or none. All means if your strength of stimulus, suppose this is the point of stimulus, if your strength of stimulus is adequate so that the membrane voltage is crossing the threshold, then the action potential will be generated, and it always generates with the maximum amplitude. Means that is the meaning of all. Means if it is happening, then it happens with maximum strength. That is all. Happening with maximum strength. And if the strength of your stimulus is not adequate, means the membrane voltage is not crossing the threshold, it is below threshold, then no action potential is going to happen. Means if it is happens with the maximum strength, and if your stimulus strength is not adequate, then no action potential at all. Means smaller version of action potential is not possible. If it is happening, then happening with the largest version, and that is the plus 35 millivolt. That's why this all means if it is happens with maximum strength, and none means not at all if the voltage is not adequate. That is the meaning of all or none law, right? So got it? So this is the concept of your local potential or graded potential, and how the action potential is generated from there. Now, another property of the local potential, which I have not discussed yet, that is known as 5. That is summation of local potential. Summation of local potential. So summation means it is nothing but addition. Two local potential. Suppose one local potential strength is 5 millivolt and another local potential strength is 5 millivolt. They can simply add up with one another, and they can give a voltage of plus 10 millivolt. That is the meaning of simple summation, right? That is the meaning of simple summation. Action potential will not have this kind of property. Action potential cannot sum it up, right? If you generate one action potential and another action potential, they cannot sum it up with one another, and it cannot give rise to plus 35 millivolt, right? Not possible. So the summation occurs in case of local potential. We have to understand two types of summation. One is known as temporal summation, and one is known as spatial summation. Okay, so now we are going to discuss this temporal summation and spatial summation with the help of a diagram, right? So again, the same thing, the neuronal cell body. Okay. So this is the neuronal cell body. Good, beautiful diagram, right? So now here the excitatory neuron. Right. So now this excitatory neuron has produced one local potential, and the strength of that local potential is plus 10 millivolt. Okay, so what I am saying that suppose this excited neuron has produced one local potential, and the strength of this local potential is plus 10 millivolt. Okay, I am not looking at the membrane potential, I am looking at the strength of the local potential. What is the voltage? What is the charge of this local potential? That I am looking at. Now I told you the local potential means that is a decremental potential. Decremental potential means after stimulation, if you stop stimulation in between, then this 10 millivolt voltage will die at the same area. How it will die out? It will die out by leakage of ions from the cell body. Gradually more and more ion will leak from cell body, and what will happen? The voltage, the positive voltage that has been generated, okay, suppose that is due to sodium, then the sodium will leak out from cell, and gradually this local voltage will die out at the same area. Same area means exactly in the same area? Answer is no. Local potential can move a little bit, but that movement is never long enough. Please note down. So I told you that action potential is a propagated potential. What do you mean by that? It means if the action potential is generated here, it can go up to the terminal part of the neuron. But if the local potential is generated here, it can never move up to the terminal part of the neuron. That means local potential can move, but a very short distance. Very short distance means, is there any definition? Answer is yes. Why not? Okay, I'll give you definition. Just hold on. So local potential, whenever it is trying to move from one area to the other area, there will be gradual decrement. And there is a definition that at which distance, so it is moving, at which distance the local potential reduced to 37% of the original voltage. Okay, again I am repeating, the distance at which local potential reduced to 37% of original voltage. This is the definition of physics. 37%, where from it is coming? This is from the definition of physics. Okay, that is a length constant, time constant definition, right? So the distance at which the local potential reduced to 37% of the original voltage, that distance is known as length constant. That distance is known as length constant. So the length constant is denoted by lambda. Lambda is equal to distance at which the local potential reduced to 37% of the original. So if the original voltage is 10 millivolt, it will reduce to 3.7 millivolt. Okay, at which distance? That is nothing but lambda. In case of neuron, generally the lambda is 1 to 2 millimeter, right? Getting my point? So the lambda is generally 1 to 2 millimeter in case of neuron. But by this way, you can calculate that a certain amount of local voltage, how much distance it can travel, but it will never be a long distance. Okay, so this length constant concept is very important to understand the summation. Similarly, Similarly, suppose the local potential is not traveling at all, it is remaining in the same area, then also it can reduce to original voltage over time. What I'm saying? So if the local potential is trying to travel, then also it will decrease, and if it is not traveling at all, then also it will reduce in the same area over time. So if I calculate the time at which it reduced to 37% of the original, that will be known as the time constant of the local potential. Time constant is nothing but denoted by tau, okay, and this tau is equal to time at which the local potential reduced to 37% of the original, right? So these two important concepts are very important, okay. It is also given in GNOME, so at any point of time the question may be given from here. So now what I will do with the concept of this length constant or time constant. If you want to understand summation, these two concepts are very essential. Why? Now look at this diagram. So again the same diagram, okay, neuronal cell body, okay, neuronal cell body, same kind of diagram, okay. Now here is the neuron which is giving stimulation, but in these cases I will give two stimulation in a quick succession. Okay, so this neuron is giving stimulation. I'll give two stimulation by this excitatory neuron in quick succession. Okay, so suppose in first stimulation, the local voltage which is generated here, okay, that is plus 5 millivolt, right? So we just understood that this plus 5 millivolt, this local voltage will decrease over time or decrease with a little distance. But before the decrease of this 5 millivolt, if I give a second stimulation, so one stimulation, okay, that has generated plus 5 millivolt. Now I am giving a second stimulation before the decrease of the first local voltage. So again the second stimulus is generating plus 5 millivolt. So these two membrane voltage will sum it up with one another, and suppose the threshold voltage of this neuron is 10 millivolt, then obviously this will be able to produce an action potential on this neuronal membrane. That means what I am saying that these two local potential, they are summated up with one another over time. But what should be the length constant for this kind of summation? Okay, then what will happen whenever this plus 5 millivolt local potential is generated? If the time constant, okay, if the time constant is very short, then what will happen? This 5 millivolt will immediately reduce to 0 millivolt over a short span of time. Okay, it will reduce to 37% and then to 0 over a short span of time. That is the meaning of short time constant. Then if you give this second stimulus, then the summation is not going to happen. But if the time constant is long enough, then what will happen? The first 5 millivolt that has been generated, it will remain there for long time, and by the time if you give a second stimulus, the second stimulus will add up with the first stimulus, and then summation is going to happen. That means if you give two stimulus and if you want them to sum it up with one another, then you require a long time constant. This kind of summation where two stimulus are given, okay, over time, and the summation is occurring, this kind of summation is known as temporal summation. This is known as temporal summation property, right? So temporal summation means, just remember like this, temporal means over time, and summation means this is nothing but addition of two membrane voltage. So over time you are giving one stimulus, and then after certain point of time you are giving another stimulus in the same area. in the same area. So what is happening? These two stimulus are merging with one another over time because of the long time constant. If the time constant is very, very short, then these two stimulus is not going to add up. That's why the basic concept of temporal summation is that summation occurring over time. Okay, two stimulus, they are summated up over time if the time constant is very, very long. So please note down that for temporal summation, time constant should be very, very long enough, right? Now, what about, okay, spatial summation? Now, in spatial summation, suppose again the same thing, one neuron is here, okay, and another neuron is here. So for the spatial summation, you require two neurons. Suppose this is neuron A and neuron B, and you are giving stimulation through these two neurons simultaneously. Note down. In the temporal summation, there was only one neuron, and that was this green color neuron. Okay, and we were stimulating multiple times over time. But here, I have two neurons, and I am giving stimulation through these two neurons simultaneously. A and B, both the neurons are stimulated simultaneously. So this neuron is developing a 5 millivolt local potential, and the neuron B is also developing a local potential of 5 millivolt. Now this local potential is trying to travel. Towards the initial segment, right? If their length constant is long enough, if their lambda or length constant is long enough, then both of this potential will reach towards the initial segment and they will add up. They will add up at this area. But if their length constant is very, very short, then you will be able to understand that what is going to happen. If the length constant is very, very short, then both the local potential will try to travel, but they will not be able to meet up with one another. But if their length constant is long enough, then it will also travel a little long distance, it will also travel along, and then they will add up with one another. And this addition of those two stimulus, okay, is known as summation, and this kind of summation is known as spatial summation. What is the meaning of spatial summation? Spatial summation means, I remember like this, spatial means over space. So this neuron B and this neuron A, they are making synapse on two different space on the cell body, two different area, two different space. So the summation between two different space, that's why this kind of summation is known as spatial summation. So for the requirement of the spatial summation, what is you require? You require long lambda or long length constant you require. So for temporal summation, so if I go to the bottom line here, so for the temporal summation, I require tau, which should be very, very long, and for spatial summation, I require lambda, which should be very, very long. Temporal summation means summation over time, okay, and the stimulation is in the same area, and spatial summation means summation from two different space, that is meaning of spatial summation. Now, whenever summation is occurring, what is the ultimate target? I told you here, if you look at this diagram, what is the ultimate target? Summation is occurring, so one potential is moving from this side, another potential is moving from this side, they are adding up with one another. The ultimate target is that it will cross the threshold voltage, and after crossing the threshold voltage, the target is to opening this voltage gated sodium channel which are present at the initial segment. So if you open up all these voltage gated sodium channel, almost all simultaneously, then huge amount of sodium will enter in the cell, and that will rise the membrane voltage to plus 35 millivolt, and that is nothing but action potential, and action potential will propagate from one part to the distal part of neuron. Getting my point? So ultimately, the target of this summation is that, okay, to produce one action potential, because the local potential strength is very less, but if they are adding up with one another, then it can give rise to an action potential. So now we'll be discussing this action potential with the help of a graph. Okay, what I mean to say? I mean to say that suppose you have connected one electrode inside this cell and one electrode you have connected outside this cell, and in between these two electrode the recording screen is attached, and support this recording screen is cathode ray oscilloscope. So what you are going to find out on this cathode ray oscilloscope, I am going to get a diagram like this, and this diagram is nothing but our action potential. So what are the different parts of action potential that we are going to discuss now, right? So I am drawing one x-axis, okay, right? So this is the time axis and another y-axis. This is y-axis. It is nothing but membrane voltage axis. Membrane voltage axis, right? So this part is minus 70 millivolt. This is minus 55 millivolt. All of you know the importance of this minus 55, that is the threshold voltage, right? And this is 0 voltage, that is the ISO voltage, and above 0 another point I am giving, that is plus 35 millivolt, right? So now suppose this is the point from where I have started stimulating the neuron, stimulation point, right? So initially whenever you are giving stimulation on a neuron, okay, stimulation on a neuron means by this kind of excitatory terminal, whenever you are giving stimulation, what will happen? This membrane voltage will gradually rise towards the threshold voltage. So what kind of potential this is? What is the name of this potential? This is nothing but local potential. Now if I ask you, sir, what is the cause of this local potential? Why this local potential is generated? Why it is moving towards depolarization? It is also due to entry of sodium in most of the cases, mostly in neuron, it is due to sodium. It may be other ions also, other positive ions like calcium can also cause this local potential. But for the time being, you remember this is due to entry of sodium. But sodium will enter through which channel? Again the same thing. It is the voltage gated sodium channel which is written like this, Na.V, that is the voltage gated sodium channel opening. But please remember that in case of local potential, only and only few voltage gated sodium channel will open up. So local potential means sodium channel is opening up, but their numbers are very few, 1, 2, 3, 4 like this. The sodium is entering in the cell and the local potential is rising. Now whenever this local potential is touching the threshold, a positive feedback phenomena will occur. What do you mean by positive feedback phenomena? We have discussed the positive feedback phenomena in general physiology. Okay, so what is that? Look at. So this local potential, okay, has already developed some kind of depolarization on this membrane. So this is my membrane, right? Okay, so the local potential, it has already developed some depolarization on the membrane. Now, if this depolarization is sufficient enough to open adequate number of sodium channel, voltage gated sodium channel, what will happen? Further sodium will enter inside the cell. This sodium will causes more depolarization. That depolarization will open up further sodium channel here. So what I am saying that little bit of depolarization is helping the opening of sodium channel. That sodium channel is causing more depolarization, and that depolarization is opening up further sodium channel. This is which kind of phenomena? This is nothing but positive feedback phenomena. And due to this positive feedback phenomena, what will happen? This opening up of voltage gated sodium channel will amplify in a significant amount, and almost all amount of voltage gated sodium channel will open up within fractions of second. Whenever you reach at this threshold voltage. So at the level of threshold voltage, this positive feedback phenomena is so strong that almost all the voltage gated sodium channel will open up within fractions of second, and that will rise the membrane voltage rapidly to plus 35 millivolt, and this rise of membrane voltage towards plus 35 millivolt is known as depolarizing phase of action potential. This is known as depolarizing phase of action potential. So if I ask you what is the cause of this depolarizing phase of action potential, it is very simple, that this is nothing but due to opening of Na.V channel. Voltage gated sodium channel opening is the cause of this depolarizing phase of action potential. Now please remember, this voltage gated sodium channel which is causing the action potential on neuron is very fast. Very fast means, what do you mean by very fast? Very fast means to open this channel, the opening of the channel require only 0.1 millisecond. Very rapid, very fast, right? And after opening, the inactivation of this channel, will occur after 1 millisecond. Getting my point? So to open the channel, to open the gate of the channel, that's why it is known as voltage gated, it requires only 0.1 millisecond. And after opening the gate, again it will be inactivated after 1 millisecond. So it remain open for only 1 millisecond. That's why the channel is known as a fast voltage gated sodium channel. Opening and inactivation is very fast, right? So what will happen? Whenever there is inactivation of the sodium channel, the membrane voltage will not rise further. So this membrane voltage will not rise further whenever there is inactivation. But proportionally, you remember that potassium channel will also open up. So if I imagine a diagram like this, that this is the neuronal cell membrane, this is the axon of the neuron, okay. So during this depolarization phase, sodium is entering during depolarization. Now the sodium channel is inactive. But already the potassium channel is open. And if the potassium channel is open, potassium is going out of the cell. So if the potassium is going out of the cell, that means the cell is losing positive charge. So what will happen? The membrane voltage will be more and more negative, and this more and more negative membrane voltage is nothing but it will look like this: more and more negative, then it will go below the RMP also, and then it will come back like this again. Okay, so again I will draw. So the membrane voltage is gradually returning, then it is going below this RMP, and then it is coming back to RMP like this. Okay, so now if I look at this whole part which I have just made, this portion of the action potential is known as repolarization phase of action potential. I told you already that what is the meaning of repolarization. So if I ask you what is the cause of this repolarization phase of action potential, you will be easily answering this question, that potassium exit from the cell through voltage gated potassium channel K.V, okay, as well as what is the condition of sodium channel? There is inactivation of voltage gated sodium channel, that is Na.V, that is already inactive, but opening of the potassium channel is the main cause of this repolarization phase of action potential. Now you also remember that this voltage gated potassium channel, they are very slow channel. So the sodium channel is very fast, but this voltage gated potassium channel, they are very slow enough. Okay, now due to slowness of this potassium channel, one important phenomena occurs in this diagram. What is that? Look at this. You can find out that one part of the action potential is going below the resting membrane potential. It is going below this resting membrane potential. Okay, ideally it should not. Go below the resting membrane potential. Why you are going below this resting membrane potential? Ultimately, you have to come back to the RMP. Okay, but this membrane voltage, which is moving below the resting membrane voltage, this part is known as after hyperpolarization phase of action potential. This is known as after hyperpolarization. Obviously, it is going below the RMP, more negative than RMP, than hyperpolarization. So this is known as after hyperpolarization phase of action potential. Now question, why there is after hyperpolarization? Okay, why? You are saying that potassium is going out and that's why the repolarization is happening. That I can understand. But why it is going for more negative? Look at this. Potassium channel is very, very slow in nature. Slow in nature means opening of the channel is very slow. Closing of the channel is also very slow. So, when the membrane voltage is returning towards this repolarization, I can understand that more and more potassium is going out of the cell. So, more and more repolarization, more and more potassium is going out of the cell. So, ideally, when the voltage is at this RMP, all the potassium channels should be closed. Getting my point? So, whenever the membrane voltage is returning towards the RMP, potassium channel is closing like this. Suppose 100 potassium channels are there, they are trying to get closed. Ideally, all of them should get closed at this area. But because of the slowness of the channel, because the channels are very, very slow, although the membrane voltage has reached to RMP, but all the potassium channels are not closed yet. Some of the potassium channels are still open. So, if some of the potassium channels are still open, some extra potassium will go out of the cell, which are not supposed to go out. Getting my point? Okay. So, although the membrane voltage has reached to RMP, potassium channel is supposed to get closed completely, but because of the slow nature of the channel, some of the potassium channels are still open. And because of this still open potassium channel, some extra potassium is going out of the cell, which are not supposed to go out. And if extra potassium is going out, the cell will lose extra positive charge. Extra positive charge loss means there will be more negative voltage, and that is nothing but after hyperpolarization. So now if I ask you, what is the cause of this after hyperpolarization? After hyperpolarization, your answer is this is also due to exit of potassium. But better answer is this is due to slow closure of potassium channel. Okay, voltage gated potassium channel. Slow closure of voltage gated potassium channel means some extra potassium will go out. So extra exit of potassium from cell, and this is leading to after hyperpolarization of action potential, right? So please remember these three basic phases of action potential: depolarization phase of action potential, repolarization, and after hyperpolarization is basically part of repolarization. After hyperpolarization, this is basically part of repolarization. Okay, and why the after hyperpolarization is happening? This is due to slow closure of the potassium channel. Now, also remember, potassium channel opening is a negative feedback phenomenon. Okay, look at this. So this is your membrane. Okay, potassium channel opens in presence of depolarization because it is a voltage gated channel. Note down, potassium channel is K dot V, voltage gated channel. Voltage gated channel means what you require to open up this channel? Voltage. What kind of voltage? Hyperpolarization? No. Voltage gated channel means you require depolarization to open up this channel. So whenever there is depolarization, the channel will open up. But whenever potassium channel is opening up, cell is losing positive charge in the form of potassium. So what will happen to the interior of the cell? Interior of the cell will be negative. So what is the effect of this negativity on further potassium channel? What is the effect of this negativity on this another potassium channel? It will open or it will close? It will close. So I can understand that opening of one channel is leading to closure of the another potassium channel. So obviously this is typical of negative feedback phenomena. Please note down that during action potential, opening up of voltage gated sodium channel, I told you already, opening up of the voltage gated sodium channel is a positive feedback phenomena, but opening up of the voltage gated potassium is a negative feedback phenomenon. So this is all about the three major phases of action potential, and you look at the complete diagram of action potential like this. Now apart from this, we have to also understand another 2-3 phases of action potential. The part of action potential which is above 0 volt, this is very simple, that we have already discussed earlier also. This is known as overshoot phase of action potential. So it is a part of depolarization which is going above the 0 millivolt, that is overshoot. Now the part of this depolarization and the part of this repolarization which is above this threshold voltage, above this threshold voltage means this area where I am giving highlight. Okay, so this area where I am giving highlight, this part which is above the threshold voltage, including the part of depolarization also, part of repolarization also, this phase is known as spike potential phase of action potential. This is known as spike potential. So basically spike potential means it is nothing but a part of action potential which is above the threshold voltage. Getting my point? So this is all about different phases of action potential. Now during action potential, just now we have discussed that various ions are entering in the cells and various ions are also going out of the cell. So now we are going to discuss another important concept, that is nothing but permeability of different ion during action potential. Permeability of different ion during action potential. So this is the same diagram, this is the time, this is membrane voltage, and I am drawing an action potential. So now you are habituated with the diagram of the action potential. So this is local potential, then after this local potential, sudden rise of membrane voltage and falling of membrane voltage like this. So this is the typical diagram of action potential. Now in this action potential, I want to look at the sodium permeability first and then potassium permeability first. Sodium channel and potassium channel opening permeability. Okay. So first sodium. Okay. So sodium channel will start opening from this part. This point means whenever there is generation of the local potential, from that point the sodium channel will start opening up. So with this green color I am drawing, so sodium channel is opening up, but I told you initially during local potential few voltage gated sodium channel will open up. So this green color curve, look at this green color curve, again I am drawing. Okay, so this green color curve indicates sodium channel are opening, very slow opening during the local potential, very slow opening during local potential. Look at slowly opening, but whenever you reaching at this threshold voltage, suddenly huge number of sodium channel will open up, and it will reach its maximum, and then suddenly all the sodium channel will be inactivated like this. So this green color curve, this is known as G of sodium curve. G stands for conductance. Conductance means it is nothing but permeability curve. Okay, so G stands for conductance of sodium. This is nothing but permeability of sodium through membrane during action potential. So if I want to understand this curve, what is the meaning of this curve? Meaning of this curve, this green color curve indicates how many numbers of sodium channels are open during action potential. So initially I can understand that initially very less number of sodium channels are open, and whenever you are reaching this threshold voltage, suddenly huge number of sodium channels are open, and then suddenly all these sodium channels are getting inactivated. That is the meaning of this curve. Means permeability is nothing but it depends on the number of channels which are open at a point of time. That will determine the permeability. So green color curve indicates sodium permeability, fast channel. Now look at the potassium permeability. So potassium channel, I told you repeatedly, it's a voltage gated channel and it's a slow channel. Voltage gated channel means opening of the potassium channel will also start from the same point where the sodium channel is opening up. Getting my point? It is also voltage gated channel, so it will also start opening up during the sodium channel opening point. But because of the slow nature of this channel, the opening will take very long time, and the closing will also take very long time. That's why the curve of potassium will look like this. Getting my point? Look at this curve. Okay, should I take a different color or this color is okay? I think this is okay. So this is the opening point, starting of potassium channel opening, very slow, very slow. Number of potassium channel opening is rising, taking long time. Again it is closing, very long time. So this curve is nothing but G of potassium, that is nothing but permeability of potassium during action potential in neuron, right? So now looking at this curve, if I ask you, during after hyperpolarization, which channels are open? Only potassium, only sodium, both of them? How to understand or how to answer this question, right? So I have to just drop a perpendicular from this, okay, like this. Then if I divide, then I can understand that during this after hyperpolarization, only and only one channel is open. Look at this. It is cutting only which curve? This is cutting only potassium curve, right? So during this after hyperpolarization, I hope you are getting. So during this after hyperpolarization, if I look at this permeability curve, it is only potassium which is permeable during after hyperpolarization. Similarly, if I ask you that during this peak of this action potential, what are the channels that are open? Then you will drop a perpendicular like this, and here it is cutting this green color curve also, here it is cutting the potassium curve also, okay, purple color curve also. So during this peak of this action potential, sodium channel is also open, potassium channel is also open, but obviously the number of sodium channel are very huge in comparison to potassium channel. That is the meaning of this permeability curve. I hope all of you are getting this concept. So from this, multiple image based question has been given. What are those questions? Okay, so questions will be like this, but before that I should put some numbers. Suppose this is A, this is threshold point is B, peak of this action potential is C, the mid part is D, this RMP part is E, and this is A point. Okay, our answering will be easier. That's why I'm giving some point. So your first question, at which point the permeability of sodium is maximum? At which point the permeability of sodium is maximum? Very simple. All of you will be able to answer. That is at point number C, right? Similarly, if the question is permeability of potassium is maximum, at which point? So obviously your point number D, right? So point number D is the maximum permeability point of potassium. I am just following the potassium curve and looking at what is the peak of this potassium curve, and that is the maximum permeability. Then third question, point at which membrane voltage close to equilibrium point of sodium. So in previous class we have discussed the equilibrium potential. Equilibrium potential means that will be calculated by Nernst equation. So what is the equilibrium potential of sodium? You recall, that is plus 63 millivolt. I told you repeatedly. In action potential, the maximum positivity that is occurring is plus 35 millivolt. Action potential, normally they will never move up to this plus 63 millivolt. Maximum they can move up to this plus 35 millivolt. Why? Because of the rapid inactivation of the voltage gated sodium channel. Sodium channel is very fast opening and very rapid inactivation. That's why the action potential, they will never rise up to plus 65 millivolt. That is the equilibrium potential of sodium. But the maximum rise of action potential is possible up to plus 35 millivolt. Okay, so action potential amplitude will never be equal to equilibrium potential of sodium, but it can move close to. It is trying to go towards plus 63 millivolt, but it is not able to go there. That's why whenever the question is point at which membrane voltage is close to equilibrium potential of sodium, then obviously your answer is again the point number C, and that C is nothing but the peak of action potential point. peak of action potential point, right? Next question, similar type of question, point at which membrane voltage close to equilibrium potential of potassium. So what is the equilibrium potential of potassium? Equilibrium potential of potassium is minus 90 millivolt. That is the equilibrium potential of potassium. I hope you remember. So in this action potential curve, I have to find out a point which is the maximum negative. Maximum negative, right? Maximum negative means hyperpolarization. So if I follow this point, if I follow this, then this is minus 70 and this point number F, which is more negative than minus 70 also. It may be minus 75, maybe close to minus 80. It will never go up to minus 90 also. So again, if the question is point at which it is close to equilibrium potential of potassium, answer is point number F. Okay, that is nothing but the after hyperpolarization part of action potential, right? 4 questions. Now another question that is more dangerous. Okay, not that much dangerous. Okay, so question is point at which sodium permeability upon potassium permeability ratio is maximum. Ratio is maximum at which point? Means if I look at point number A, point number B, point number C, I have to consider that how many sodium channels are open, how many potassium channels are open. Sodium channels are how many open, potassium channels are how many open, and I am asking maximum ratio. Maximum ratio means I have to find out a point where the sodium channel numbers are very high than potassium, and again the same answer, that is at point number C. So for sodium everything is pointing towards peak, that is the point number C. But if I reverse this ratio, now my question is the point at where potassium upon sodium permeability ratio, potassium upon sodium permeability ratio maximum. Then again I have to find out one point when potassium permeability is maximum in comparison to sodium. So obviously you are thinking that point number D will be the answer, but at point number D, if we plot a perpendicular like this, at point number D, potassium permeability is high, I can understand, but sodium permeability is also there. So potassium upon sodium, it is nothing but division of 2 number. It is division of 2 number. But if I look at after hyperpolarization point, like for example, if I look at point number F, potassium ion is permeable. But what about sodium ion permeability? Sodium ion permeability is already 0 here. So at point number F, potassium permeability is present, but sodium permeability is 0. So if you divide this K, potassium permeability, upon 0, what is the ratio? This is nothing but infinity. So obviously, whenever I will ask you a question that potassium upon sodium permeability ratio is maximum at which point, your answer is at point number F, where the ratio is infinity. Infinity means sodium permeability is 0 at hyperpolarization. Only potassium is permeable through the membrane during after hyperpolarization. Why? I told you, because potassium channel is slow. He was supposed to close, but it is not getting close, and that's why the answer is point number F. So this is all about the permeability of different ion during action potential. Getting my point? Very important, very interesting thing. Okay. Now the next point of discussion regarding this action potential is refractory period. Okay. Refractory period. You must have heard about refractory period. Okay. I'll explain. Okay. So again the same thing, I have to draw one action potential diagram. Okay, without this diagram you cannot move here and there. Okay, so this is x-axis and y-axis. Okay, now I am drawing the action potential in a little different manner. I am spreading the action potential on x-axis. Okay, so the action potential is spreaded on x-axis. Otherwise, the same action potential. Now, if I ask you that suppose this is point number A, this is point number B, this is point number C, and maybe this is D and this is E. Which one point is the starting point of action potential? Point number A or point number B? I hope all of you will answer like this, that from A to B, this is the local potential. So action potential is starting from point number B. So it is the starting point of action potential. And what is the ending point of action potential? Very simple. The ending point of action potential is point number E. So in between this, if I measure this duration, between these 2 points, beginning of action potential and ending of action potential, this will be known as APD. APD means action potential duration. So this is known as action potential duration, right? Action potential duration or APD for a neuron. It is only 1 to 3 millisecond, a very rapid signal. In case of skeletal muscle, same kind of action potential, only the duration is a little bit more, 2 to 4 millisecond. In case of myocardium, we'll discuss this action potential later on, but it is completely different and it has a plateau phase, because of which the action potential duration is very long, 200 to 400 millisecond. And for smooth muscle, the duration is variable, that is 10 to 50 millisecond depending on the different types of muscle. So this neuronal action potential, okay, this skeletal muscle action potential and this myocardium action potential, all these 3 tissues action potential is based on the same channel, that is the voltage gated sodium channel. The fast voltage gated sodium channel, same ionic basis. But why the myocardium action potential is so prolonged? Because of there is a plateau phase. We'll be discussing this later on. But for smooth muscle, the action potential is based on voltage gated calcium channel. Remember like this. So for smooth muscle, the action potential is based on calcium. But in neurons, skeletal muscle, myocardium, the action potential is based on the same voltage gated sodium channel. So now we know about the action potential duration. Now if I want to note down the duration of depolarization phase of action potential, so what I will do, I'll just drop on perpendicular from this. So I'm dropping on perpendicular from here, okay, and in between these two, okay, if I measure the time duration, this is nothing but time duration of depolarization. This is nothing but depolarization phase time duration, right? So this is the depolarization time duration, and obviously starting from here, if I measure the time up to the end of this action potential, this is nothing but repolarization time. Fine. So depolarization time, repolarization time. Now, whenever we are talking about refractory period, okay, refractory period means that period where second action potential generation is not possible or maybe difficult. What do you mean by that? Suppose I am giving you a question like this, that this is one action potential, it has been generated due to a stimulation here. This is the point of stimulation. If I give another stimulation at this point, can I get a second action potential? Answer is no. If I give a second stimulus here, can I get a second action potential? Answer is no. If I give a second stimulus here, can I get? Answer is no. But if I give a second stimulus here, then I may get a second action potential at this region, right? So based on this concept, the concept of refractory period has been developed, right? So we have 2 types of refractory period, absolute and relative. Absolute refractory period means that period of the action potential where second action potential is never ever possible, this part. And relative refractory period means that period of the action potential where second action potential is possible, but with a higher strength of stimulus than previous. I will explain. Just hold on. Okay. So first of all, I will write down like this so that you understand better. So refractory period. Okay. Absolute refractory period and relative refractory period. Relative refractory period. So absolute refractory period, relative refractory period. So first talk about the time duration. Absolute refractory period means it is the total duration of depolarization phase of action potential plus first one third duration of repolarization phase of action potential. So what do you mean by that? Means in this diagram, if I take the total duration of the depolarization plus first one third, suppose I am dividing this into three halves, so I am taking the first one third of repolarization also. So from here up to the first one third of repolarization, okay, like this. So from this up to this zone, if I give a second stimulus at any of this point, if I give a second stimulus at any of this point, I'm not going to get a second action potential, and that's why this is known as absolute refractory period of action potential, right? So absolute refractory period means, what is the meaning of this? Meaning of this is second action potential is never ever possible. Second action potential is never possible within this area. That's why this is known as absolute refractory period. Relative refractory period, now it will be simplified. So obviously the last two-thirds of this repolarization phase, that is nothing but my relative refractory period, right? So relative refractory period means last two-thirds of repolarization phase of action potential is relative refractory period. Relative refractory period ka meaning is that second action potential possible, but okay, with a higher strength of stimulus. Getting my point? Higher strength of stimulus means, suppose the previous action potential that you have generated with 5 millivolt voltage stimulus, the second action potential will be generated during relative refractory period, provided that the stimulus strength is more than 5. More than 5 means how much? It depends on different neuron, different cell membrane. But the concept of this thing is that, suppose I have given a stimulus of 10 millivolt and I have generated this action potential, right? If I give any kind of stimulation, maybe 10 kilovolt, okay, maybe 10 megavolt, maybe 10 megavolt stimulus in this area is absolute refractory period area. Second action potential is never ever possible. But if I give a second stimulus here with same 10 millivolt voltage, then no action potential is going to happen. But if I give a second stimulus here or here with maybe 10 megavolt or with maybe 10 kilovolt, then the second action potential is possible. That is the meaning of a relative refractory period, right? So absolute and relative refractory period meaning you know, and what is the time duration you know. So this kind of image will be given and they will give you that if I give a second stimulus here, second action potential is possible or not? Your answer is no. If I give a here, then second action potential is possible, but with higher strength of stimulus. Now question, why the neuron is behaving like this, sir? Absolute relative means basically you are asking what is the cause of this absolute and relative refractory period? Yes, answer is yes, yeah. So to understand this concept, you have to understand the different stages of voltage gated sodium channel. So voltage gated sodium channel. right? Different stages of voltage gated sodium channel. Na dot V, right? So voltage gated sodium channel means it will have gate. So suppose this is the membrane, this is the cell membrane. On this cell membrane, I am drawing one voltage gated sodium channel. So this is my voltage gated sodium channel, right? Okay, so it will contain two gate. So one of the gate is known as M gate. So this is M, right? So M gate is blocking this inner mouth of this channel. It is blocking the inner mouth of this channel. Okay, and there is another gate. This gate is H gate. H. Okay, so when the membrane is at resting membrane voltage, when the membrane is at resting voltage, means inside is negative and outside is positive. We know this thing. Inside is negative and outside is positive. This is the resting stage of the membrane. What will happen? The sodium channel, two gates are there, but between these two gates, M gate is blocking the inner mouth of this channel. So can sodium enter through this channel? Answer is no. Sodium will not be able to enter through this channel. Means this is the stage of the channel which is known as the closed state of the channel. This is known as the closed state of the channel or closed stage, right? So close means the M gate is blocking the mouth. Now I am causing the depolarization of this membrane voltage. So again the same thing, the cell membrane. Okay, so on this cell membrane the voltage gated sodium channel is here. Okay, now I am causing depolarization of this membrane. Depolarization of this membrane by stimulus. So depolarization means we know that there will be positivity inside. So this is depolarization. Now whenever there is depolarization, remember that this M gate, this is nothing but a protein. Na? The channel is like a protein. So M gate means this is a part of the protein molecule only. Protein molecule means it is composed of amino acid. The amino acid which are present at the surface of this M gate, it is a positively charged amino acid. So this is a positively charged amino acid present on the surface of this M gate. Positively charged amino acid present on the surface of this M gate. So what will happen? Whenever this inner membrane voltage is becoming positive or depolarization, this positivity will causes repulsion of this M gate positive charge, because of which the M gate will be shifted away from the mouth of this channel. And whenever M gate is shifted away, already our H gate is away from this channel. So already the H gate is away from the channel from the previous stage. So H gate is already away from the mouth. Now the M gate has just shifted from the mouth. What will happen? The channel will be open up, and due to opening up, the sodium start entering in the cell. Huge amount of sodium will start entering in the cell. This stage is known as open stage of voltage gated sodium channel. So from this closed state, open stage, how much time is required? This is very, very fast. I already told you, only 0.1 millisecond time is required. So within this 0.1 millisecond time, the closed state is converted into open stage, okay, by shifting of the M gate away from the mouth. Now, this open stage will remain for short duration, and that duration I also told you, that is for 1 millisecond. So after 1 millisecond, again this is my cell membrane, okay, again this is my cell membrane. On this cell membrane, this is my voltage gated sodium channel. Now imagine that membrane voltage is still in depolarized condition. So the membrane voltage is still positive, okay. So if I maintain this depolarization for a long time, that is the meaning. If I maintain the membrane depolarization for a long time, what will happen? Will the voltage gated sodium channel will remain in the open state? Answer is no, no, no. what is going to happen? Now this H gate, it will come close to this mouth, and now the H gate is going to causes block of this inner mouth of the channel. Although the M gate is still away from the channel, but it doesn't matter because now the H gate has get its place and H gate is shifting towards the mouth, and now the H gate is basically blocking the inner mouth of this channel. Again, the sodium will not be able to enter through this channel, and this stage is known as inactive. This is not known as closed. This is known as inactive stage of voltage gated sodium channel. So, if the membrane voltage remain in depolarized condition till the sodium channel will move from this open stage to this inactive stage after 1 millisecond time duration. So that's why I told you the voltage gated sodium channel remain open for 1 millisecond. After 1 millisecond, the open channel will move to inactive stage. Inactivation occurred due to movement of the H gate into the mouth. Right. Now the question, can I open this inactive channel once again? Means, is it possible to move this inactive stage to open stage bypassing the closed stage? Answer is never ever possible. So what I am saying, can I open a inactive channel directly to the open stage? Answer is this is never ever possible. That's why if a voltage gated sodium channel is inactive, you cannot open up this inactive channel directly. What you have to do? You have to wait for some time, and by the time this inactive channel will again move to closed stage, and then only again you can open this channel once again. That means if I want to open up one inactive channel once again, this inactive channel has to move through first closed stage and then from closed stage to the open stage. So the time when the voltage gated sodium channels are inactive, almost all the channels are inactive, can you open them once again? Answer is no. So can you generate a second action potential? Answer is no. That's why the answer of this absolute refractory period means your explanation will be that most of the Na dot V either are in inactive stage or they are already in open stage from the previous action potential. So if the channel is already open, you cannot open them further because already open, that's why the action potential is going on. And if the channels are inactive stage also, you cannot open them further. You have to wait for some time, and that time when you have to wait for this inactive channel to become closed once again, that is the time which is known as the absolute refractory period. So absolute refractory period means what is the status of voltage gated sodium channel? Almost all of them either in the inactive stage or in the open stage. Now a relative refractory period means most of Na dot V, okay, has moved from inactive to closed stage. Inactive to closed stage. Most of the channel has moved from inactive stage to closed stage, and that period will be known as relative refractory period. Look at this. Okay, I'll explain with some number. Okay, so suppose I have 100 numbers of voltage gated sodium channel in resting stage. If I open from 100 to 70, okay, then the action potential will be generated. Means 70 is the threshold number of channel. So within 100 resting channel, I have opened up 70 and the action potential is going on, right? Now whenever all these 70 channels are in inactive stage or in this open stage, this is the period which is known as the absolute refractory period. Okay, so within this 100, I have already opened up 70. 30 are still in the resting condition, right? Now from this 70 inactive channel, more and more will move to the resting condition or closed condition. Suppose from this 70, most of them 40 has moved from inactive to closed state once again. So now the total number of resting channel are 40 plus 30, that is 70. That means if I open up all of this 70, again I can get a second action potential, but provided you have to open all of them, 40 plus 70, all of them you have to open up, and then only you will be able to cross the threshold. Initially, if you are opening within 100, you are opening only 70% channel you are opening up. Now within this 70, you are going to open up all the 70, means now we have to open up 100% channel which are there in the resting stage. So if I want to open up all of this 100% channel, do I require less amount of stimulation or more amount of stimulation? Obviously more or higher amount of stimulation you require, and that's why I told you that relative refractory period means second action potential is possible but with a higher strength of stimulus. This is the meaning of relative refractory period. Getting my point? So this is all about your absolute refractory period, relative refractory period, everything we have discussed. Okay, so we are almost going to finish up this action potential discussion, but before finishing, one thing, that is the last thing. Suppose one problem is given that in case of hyperkalemia, so one pathological condition where extracellular potassium is very high, potassium in the ECF is very high, that is hyperkalemia. Okay, blood potassium is very high. What is going to happen? Okay, what will happen to RMP? What will happen to action potential? So to understand that, okay, I am drawing one cell. Suppose this is the cell. It may be a neuron or it may be a myocardium, whatever. Okay, so normally during RMP discussion, we have discussed that RMP is generated due to, okay, leak potassium channel. I hope you remember the name, leak potassium channel, through which potassium moves out of the cell and corresponding negative charge will be deposited. We have discussed this thing. So due to this hyperkalemia, extracellular potassium concentration is very high, and this extracellular potassium concentration is a pathology, huge amount of potassium in the extracellular fluid. So what do you think? This diffusion of potassium from inside to outside, it will be more or less? That is the only one thing you have to understand. So whenever there is development of this hyperkalemia, a new equilibrium will form. In that new equilibrium, the movement of the potassium from inside to outside will be lesser because outside potassium charges is very high. So that will prevent the movement of the potassium. So I can understand more potassium will stay back inside the cell. Ideally, this potassium should go out, but because of the extracellular hyperkalemia, it is keeping inside the cell, it is remaining inside the cell. So extra potassium means extra positive charge. That means cell membrane will be more and more positivity. Means I can understand that hyperkalemia means what will happen to resting membrane potential? RMP will be depolarized. Depolarize means that is decrease in RMP or increase in RMP. That is nothing but decrease in RMP. I hope you remember the concept, that is decrease in RMP. So please remember, this question has been asked multiple times. Hyperkalemia means there will be decrease in RMP or there will be depolarization. Now, if there is depolarization, what will happen to the voltage gated sodium channel? Just now we have discussed voltage gated sodium channel. Suppose this is my Na.V. Now tell me, this Na.V channel will remain in which stage if there is persistent hyperkalemia? So persistent hyperkalemia means there is depolarization of the membrane. So you may thinking that depolarization means that is good, sir, that will lead to action potential. Yes, initially few action potential will be generated on this cell. But if this depolarization is not corrected for long time, that means if you don't correct this hyperkalemia, then the depolarization will also not be corrected, because this depolarization is due to pathology, that is hyperkalemia. So if you don't correct the hyperkalemia, the depolarization will be persistent, and persistent depolarization means, could you tell me which stage of voltage gated sodium channel will persist? So I told you already that initial depolarization will causes opening up of the channel, but just after opening, there will be inactivation of the channel if the depolarization is still present. That means long-standing depolarization, if it is present in the cell membrane, the voltage-gated sodium channel will be inactive. If the voltage-gated sodium channel is inactive, can you open up this channel? Answer is no. Can you generate one action potential? Then answer is no. Because of no action potential, what will happen? Suppose this cell we are talking about is nothing but myocardium. So what will happen? If there is a pathological hyperkalemia, there will be initial few action potential on the myocardium, but persistent depolarization will leads to inactivation of the voltage gated sodium channel, and inactivation of the voltage gated sodium channel means no action potential. No action potential means no systole is going to happen. No systole means the heart will stop, and the stopping of the heart will occurs in case of diastole. That's why we say that severe hyperkalemia may leads to asystole of the heart, and this is the reason. What is the reason? Reason is that inactivation of the voltage gated sodium channel due to long-standing depolarization. Getting my point? So we know hyperkalemia is a problematic. So what about hypokalemia? Is that problematic also? Answer is yes, that is also problematic, but the reason is different. So suppose there is an hypokalemia. Okay, so extracellular potassium is lower than normal. Again there will be problem. Now first you tell me what will happen to RMP in this condition. What will happen to RMP? Very simple. So outside potassium less mean, okay, through this leaky channel more number of potassium will go out through this leak channel. So cell will lose more potassium. There will be more negativity inside. More negativity inside means this will leads to hyperpolarization. Hyperpolarization of the RMP. Hyperpolarization means that is nothing but increase in RMP. Now, if the membrane voltage is going towards hyperpolarization, what do you think? Action potential generation will be easier or action potential generation will be difficult? Very simple question. RMP is going towards negativity. Means, is it going towards threshold voltage? Answer is no. If it is going away from threshold voltage, then action potential generation will be easier or difficult. That's why the action potential generation will be difficult, and that is the reason why the hyperkalemia, okay, why the hypokalemia is problematic. But still there is another reason, that is that hyperpolarization is also a inhibitor of sodium potassium ATPase pump. So if your sodium potassium ATPase pump is inhibited, then you can understand that your energy source of the cell will be deficient, and that will leads to again serious kind of problem. So that's why the hypokalemia is also a problematic for myocardium cell and other cell also. Okay, and that problem is due to inhibition of the sodium potassium ATPase pump, and that is due to hyperpolarization per se. But hyperkalemia, that is more severe condition, because in that cases action potential generation will be inhibited completely. Getting my point? So this is the thing that you must have to remember, that what will happen in case of hypokalemia and hyperkalemia. Now the last one is hypocalcemia. Hypocalcemia. Okay, extracellular calcium is very, very high in comparison to intracellular calcium. But if your blood calcium or extracellular fluid calcium is going down, that is hypokalemia. Okay, so in hypokalemia, what kind of problem will arise? Right, to understand that, I am drawing on membrane, cell membrane, maybe neuronal membrane. So this is neuronal membrane. On this neuronal membrane, I am drawing on voltage gated sodium channel. So this is my Na.V. Okay, so normally the extracellular mouth of this voltage gated sodium channel is occupied by calcium ions. What I told? Now very different thing. This is a voltage gated sodium channel, so there will be M gate and there will be H gate, everything is there. But now I am saying the extracellular mouth of the voltage gated sodium channel is normally partially occupied by calcium ions. When the blood calcium is normal. So when blood calcium is normal or blood calcium is high, then and then only this blood calcium will remain attached on the extracellular mouth of the sodium channel. So if the calcium is attached on the extracellular mouth, I can understand that it is reducing the pore, reducing the channel diameter. So what will happen? The sodium will be able to enter, but it will enter with a little difficulty, right? So action potential will be generated, but that will generate with a little difficulty. But now suppose the blood calcium is less, blood calcium is low, decrease. So what will happen? Now the main target is to maintain the blood calcium, not to occupy this voltage gated sodium channel. So what will happen? The calcium which was attached here, this calcium will be detached from this voltage gated sodium channel. There will be detachment of this calcium. And because of the detachment, I can easily understand that this mouth, the pore of this channel, voltage gated sodium channel, will be open up. Okay, there will be increase in pore. So the sodium entry will be easier. And because of this easier sodium entry, I can say like this, that the sensitivity of this Na.V will be increased, and because of the increase in sensitivity, the action potential generation will be easier, okay, and that will leads to increase excitability, of neuronal membrane. Okay, so please remember, this is the reason why the hypocalcemia causes tetany. All of you know that hypocalcemia, when it is very serious, it can causes tetany. And tetany means if you give a stimulation here, your facial muscle will start forming spasmic contraction. If you give compression on your nerve, there may be spasmic contraction of this hand. Okay, chopstick sign, okay, Trozier sign, you know from your medicine knowledge. So this tetany feature, there is spasm of the muscle. Why the muscle is contracting? Per se, there is no problem inside this muscle, but the neuron which is supplying this muscle, that neuron is hyperexcitable. Getting my point? So in case of hypocalcemia, the skeletal muscle is not at a fault. There is no problem inside skeletal muscle. But the neuron which is supplying that skeletal muscle, if you stimulate this neuron will generate action potential easily. So whenever I am giving stimulation, I am giving stimulus to the neuron. Neuron is firing action potential easily. Normally it is not firing action potential, but whenever there is hypocalcemia, because of increased excitability of this neuronal membrane, the neuron will produce action potential. That action potential will stimulate muscle, and muscle will cause contraction because no problem in the muscle. If the neuron is giving stimulation, muscle will say yes, I will contract, and that contract will lead to spasm either in the hand or in the facial muscle. And that is the reason why there is spasm, okay, spasmic contraction of skeletal muscle in hypocalcemia. This is no problem of skeletal muscle. This is the increased excitability of neuron, and that is due to calcium removal from extracellular mouth of voltage gated sodium channel, right? So that's why you know कि hypercalcemia, when the calcium is very high, hypercalcemia, okay, it is an membrane stabilizing agent. You will read in pharmacology. Okay, so hypocalcemia means membrane will be excitable, and if the calcium level is high, then it will causes blocking of the extracellular mouth of the voltage gated sodium channel. So what will happen? The membrane will be stabilized. Action potential generation will not be easier. That is known as the membrane stabilizing property of calcium. Higher calcium means membrane stabilizing agent. It is said that magnesium also has similar kind of membrane stabilizing property, but the effect is lesser in comparison to calcium. Okay, and that's why even if the magnesium is deficient in your body, it can lead to severe intractable epilepsy or seizure disorder. Because same like if the hypocalcemia is there or hypomagnesemia is there, the neuron will be more excitable, and that can precipitate seizure disorder or epileptic disorder, right? So this is all about action potential and certain applied aspect of action potential.